Dear students, how are you? I hope all of you are fine. Welcome to my today's class. First I am going to do the myself introductions. My name is Narasimha, working as a physics lecturer in Government PU College, Hiriyadka, Udupi districts. Today I am going to discuss about chapter known as Nuclei. I think last part one chapter of the second PUC portion, isn't it? Now I am going to discuss the very brief synopsis of this chapter. Because why brief? Because you already written a board examinations. All of you know very well about this chapter. That is why I am not ready to waste my much time on discussion of the synopsis. I have to focus more on what discussion part of this paper. Okay, that is why I am going to discuss the very brief synopsis. Means only important conceptual points and some of the important formulas essential for a compute examinations. Okay, let us start now, students. So we know chapter name is what? Nuclei. Synopsis. You know what is nucleus? I think nucleus of an atom of atomic number Z, mass number A, is represented by means of, we know Z before that, nucleus of an atom of atomic number Z and mass number A is represented by ZXA. So what is Z here? Atomic number. A is nothing but what? Mass number, isn't it? So number of the neutron present in a atom of atomic number Z and mass number A is given by N is equal to A minus Z. So N is the number of neutrons, A is the mass number, Z is the atomic number. Depending upon the NAZ, the nuclei classified into three types, isotopes, isobars and isotones. Students, in nuclear physics, means especially modern physics, smaller values of the masses are very common. For example, that mass of a electron is of the order of 10 power of minus 31 kg. Mass of proton and neutron of the order of 10 to the power of minus 27 kg. See, in order to measure the smaller values of masses, kilogram is not a suitable unit, isn't it? So to measure the smaller values of masses in atomic physics, means nuclear physics, a special unit known as atomic mass unit is defined, isn't it? That is given by AMU. So what is 1 AMU? 1 by 12th mass of 1 atom of carbon isotopes. Its value of the 1 AMU is what? 1.60 10 power of minus 27 kg. In terms of this AMU, we express the mass of proton, neutron, etc. So we studied some of the important characteristics of a nucleus. Nuclear charge, nuclear size, nuclear, isn't it? So what is size? Nucleus is spherical in shape. The radius of a nucleus of a atom of mass number A is given by R is equal to what? R is equal to what? R naught into R is equal to R naught into A to the power of 1 by 3, where R naught is a constant. So charge of the nucleus is given by Q is equal to plus Z into V, where E is magnitude of charge of an electron. 1.6 10 to the power of minus 19 coulomb is magnitude of what? Charge of electron, isn't it? We know in nuclear physics, Einstein's mass energy relation plays one of the important vital role to measure energy, isn't it? I think it looks like a simple one, but it is one of the very important formula to study certain aspects of the nuclear physics. See, according to the Einstein, so energy equivalent of the mass M is given by E is equal to mc square. So by using this formula, we will get energy equivalent of 1 AMU is given by 931.3 mega electron volt. See, we know in a nucleus, isn't it? In nucleus, while nucleons, what are the nucleon, students? Nucleus consisting of protons and neutrons, collectively called what? Nucleons. So we know in a nucleus, protons and neutrons are held together to form a stable nucleus. While fusing these protons and neutrons, there is a loss of some mass. That loss of mass is nothing but what? Mass defect. So what is mass defect? Some of the, that is difference of the mass between sum of the masses of constituent nucleus and actual mass of nucleus. See, it is what mass defect. That is mass defect of a nucleus of mass number A, atomic number Z is given by Z into MP plus A minus Z into Mn minus M. We know where MP and Mn are the mass of proton and neutron. So M is nothing but what rest mass of the nucleus. Means there is what loss of some mass. There is a loss of mass means there is a loss of energy while forming stable nucleus. How much energy is lost? That is equal to what? By law of conservation of energy, energy required to fuse nucleons to form a stable nucleus. How much energy required to fuse nucleons to form a stable nucleus? That is equal to by law of conservation of energy. That is the energy required to split a nucleus into constituent nucleus. That is nothing but what? Binding energy. The binding energy of a nucleus is given by delta M, means mass defect into 931.3 mega electron volt. It is the what? Binding energy of the nucleus. We know binding energy of the nucleus is the measure of what? Stability of the nucleus. Got it? Stability of the nucleus. That is, so the binding energy means total energy with which nucleons are bunds together to form a stable nucleus. That is minimum energy required to split a nucleus into constituent nucleons. That is called binding energy. No amount of energy means minimum amount of energy required to remove a nucleon from the nucleus of an atom is nothing but what? Specific binding energy. So what is specific binding energy? Binding energy per mass number. See, both binding energy and specific binding energy are the measure of what? Stability of the nucleus. It means that what? If binding energy per nucleon is more, then said to be nucleus is more stable. If it is less, said to be what? Unstable or less stable. Got it here? Next one. See, we know once again, if M is the atomic mass and A is the mass number, then we can define what? Packing fractions. So what is packing fraction? See, M minus A by A. What is A? M here? Mass of the nucleus. A is nothing but what? Mass number, isn't it? That is M minus A by M. That is called packing fraction. Once again, packing fraction is what? Measure of stability of the nucleus. Remember students, if packing fraction is negative, then nucleus has to be more stable. If packing fraction is positive, then nucleus is said to be what? Less stable. It means that packing fraction may be negative or positive. Got it? Packing fraction may be what? Negative or positive. It is about what? Certain characteristics and aspects of the nucleus. There is a lot of things that we know: nuclear forces, nuclear density, nuclear mass. Okay, these are all important conceptual points. You know already about this one. Now, we know there are some, that is, we know light nuclei according to the our binding energy core. You know what is binding energy core? I think you already studied about it in your regular classes. A graph obtained by plotting the variation of the specific binding energy with the mass number is nothing but what? Binding energy curve. So from that binding energy curve, we studied that specific binding energy of light nuclear low, so they are unstable. Heavy nuclear low, so they are unstable. Intermediate nuclear having what? More binding energy per nucleon, so they are what? Stable. So because of the instability of the light nuclei and because of the instability of the heavy nuclei, it is possible to explain what? Nuclear fusion and fission. So what in Kannada? Nuclear na sanyojane, nuclear na vibhajane. Got it? So what is nuclear fusion? See, nuclear fission is what? Phenomenon of splitting of a heavy nucleus into two light nuclei with release of energy. What is fission? That is the phenomenon of splitting of a heavy nucleus into two light nuclei with the release of energy. It is called what? Nuclear fissions. So it is one of the important example, you know, standard example, when 92 uranium-235 is bombarded with fast moving neutron, resulting fragments are 56 barium-141 and 36 crypto-92 along with neutron and release of energy 200 mega electron volt. Isn't it? It is one of the standard one. See here, see, when one uranium-235 undergoes fission, how much amount of energy is released? 200 mega electron volt of energy. That is, it is about nuclear fission. Now, nuclear fusion is what? Phenomenon of combining of two light nuclei into a heavy nucleus with the release of energy. It's called what? Nuclear fusion, combining. ನ್ಯೂಕ್ಲಿಯರ್ನ ಸಂಯೋಜನೆ, ಕಂಬೈನಿಂಗ್ ಆಫ್. For example, when 4 protons are combined together to form a helium nucleus, see, along with the helium nucleus 2 positron, along with 2 helium nuclei and positron, 26.7 mega electron volt of energy released, students. In our previous slide we studied that, see, in order to release energy 200 mega electron volt, how much mass number is participated? 236. So 236 mass number is participated. So how much energy released to 200? Therefore, what is the energy per unit mass? Energy per unit mass is given by 200 divided by 236. I think it is what? Less than 1 mega electron volt. It means that energy released per unit mass. Energy released per unit mass in case of nuclear fission is less than 1 mega electron volt, students. Why I am stressfully saying this? Because here by the participation of the just 4 nucleon, it releases how much energy? 26.7 mega electron volt. It means that what is the energy released per fission of 1 nucleon? That is what? 1 nucleon. It is given by what? See, 26.7 divided by 4 mega electron volt. That's equal to nearly what? Greater than 6 mega electron volt, isn't it? Greater than 6 mega electron volt. It means that energy released per unit mass in fusion is greater than energy released per unit mass in fission. It is one of the very important conceptual points, students. We know in case of nuclear fission, in our previous slide we studied that when uranium-235 bombarded with the fast moving neutron, it splits into what? Barium-141 and 36, krypton-92. But here, in order to fuse to right nuclei, it requires what? External energy. But it needs to overcome what? Potential barrier at the surface of the nucleus. How much energy required? If we supply the energy in the form of heat, students, it requires temperature of to more than 10 to the power of 9 Kelvin. So that nucleons can enough kinetic energy to overcome electrostatic repulsion. Hence, it is also called what? Thermonuclear reactions. What is called by thermonuclear reaction, students? Because it is possible to do nuclear fusion by heating to very high temperature. Therefore, this nuclear fusion means thermonuclear reaction taking place only in the core of the water star, student. It is about what? Nuclear fusions. Now I am going to what? Next topic of the chapter. What you know? Radioactivity. So what is radioactivity? We know radioactivity is the what? Phenomenon of spontaneous, because we studied, I think. Because we know what heavy elements are, I told you, that is binding energy per nucleon of heavy elements are less. So heavy elements are unstable. Because of the instability of the heavy element. Instability means ಒಬ್ಬ ಅಸ್ಥಿರ ಅಂತ ಹೇಳಿದರೆ ಅರ್ಥ ಎಂಥದ್ದು? ನಿರಂತರವಾಗಿ ತನ್ನ ಶಕ್ತಿಯನ್ನು ಕಳ್ಕೊಳ್ತಾನೆ. So in nuclear physics, as it loses its energy, it loses its mass. As it loses its mass, we know in a periodic table, in Kannada, ಆವರ್ತಕ ಕೋಷ್ಟಕದಲ್ಲಿ ಪ್ರತಿಯೊಂದು ಮೂಲಭೂತ ವಸ್ತುವನ್ನು ಅದರ ಮಾಸ್ ನಂಬರ್ ಅನುಗುಣವಾಗಿ ಜೋಡಿಸಿದ್ದಾರೆ, isn't it? That is, as it loses its masses, it forms to what? New element. It forms what? A new element. That is why that's called radioactivity. So what is radioactivity? Radioactivity is the phenomenon of spontaneous disintegration of nucleus of heavy element by the emission of certain penetrating radiations. So who discovered it? Henry Becquerel in 1896. Got it? So the penetrating radiation emitted by the radioactive substances are classified into what? 3 types: alpha particle, beta particle, gamma particles. We know, see, when the nucleus of a radioactive element emits an alpha particle, resulting element has a mass number less by 2. Mass number less by 4 unit and atomic number less by 2. ಅಂದರೆ ಒಂದು ಮೂಲ ವಸ್ತು ಅಲ್ಪ ಪಾರ್ಟಿಕಲ್ ಎಮಿಟ್ ಆದಾಗ ಅದರ ದ್ರವ್ಯರಾಶಿ ಸಂಖ್ಯೆ 4 ಕಡಿಮೆ ಆಗುತ್ತೆ, ಪರಮಾಣು ಸಂಖ್ಯೆ 2 ಕಡಿಮೆ ಆಗುತ್ತೆ. ಸೊ ವಿಚ್ ನ್ಯೂಕ್ಲಿಯೈ ಹ್ಯಾವಿಂಗ್ ಎ ಅಟೋಮಿಕ್ ನಂಬರ್ 2 and mass number 4, that is nothing but what? Helium nucleus, 2He4. Therefore, alpha particle is identified as what? Helium nucleus. That is, in general, ZXA, I took here Z is the what? Atomic number, A is what? Mass number. Got it here? So X is what? Chemical symbol. So ZXA, Z minus 2, A minus 4, Y. That is what? A daughter element. You know what is daughter element? Newly formed element is nothing but what, students? Daughter element. During the transformation from parent element to daughter element, every loss of sign should be what? Conserved. There should be a conservation of energy, mass, momentum, etc. etc. See, for example, when 92 uranium-238 is undergo alpha decay, when it emits alpha particle, see, newly formed element is given by 90 thorium-234 plus 2He4. Therefore, what is the alpha particle? Alpha particle itself is nothing but what? Helium nucleus. Therefore, what is the charge of the alpha particle? So, charge of the alpha particle is given by 2 times the charge of the protons. And what is the mass of the alpha particle? Mass of the alpha particle is nothing but what? 4 times the mass of the what? Proton. It is about what? Alpha particle. Got it here? What is alpha decay? When the nucleus of the radioactive element emits an alpha particle, newly formed element has atomic number less by 2, mass number less by 4. It means that there is change in both atomic number and mass number due to emission of what? Alpha particles. Got it? Now next one. See, when the nucleus of radioactive element emits the beta particle, newly formed element has the same mass number, but atomic number increases by 1. It is nothing but what? Beta particle. Especially it is called as what? Negative beta particle. So beta decay itself is nothing but what? Negative beta decay, students. Remember, it is very important to note these ones. Beta decay itself is nothing but what? Emission of electron from the nucleus. It is what? That is electron. That is beta decay is nothing but what? Emission of electron from the nucleus. Example, when 90 thorium-234 emits a beta particle, newly formed element is 91 protactinium-234, so emits what? Beta decay. Got it? Similarly, one more beta decay is there. For example, that is when the nucleus of the radioactive element emits a positive beta particle, say beta plus. Newly formed element has the atomic number less by 2, same mass number. Therefore, here positive beta particle is nothing but what? Emission of positron from the nucleus. So, positron. Example is there. We know, I think. That is 11 sodium 22. When 11 sodium 22 emits the positive beta particle, then newly formed element is what? 10 neon 22. Isn't it? Plus 1 positron. Plus 1 positron. It is called positive beta decay. It is nothing but negative beta decay. Beta decay itself is nothing but what, students? Negative beta decay. Beta particles nothing but what? Electron. Remember. Next we know gamma decay. We know gamma is what? Most intense beam of light coming out from the what? Nucleus of the radioactive. It is called gamma decay. I think you know here. See, gamma rays are emission of that is in electromagnetic waves chapter studied more about gamma particle. I am not going to discuss much about this. Next we know radioactive decay law. So what is the limit of the radioactive decay law? According to radioactive decay law, we know, I think, the rate of decay of the radioactive substance at any instant is directly proportional to what? Number of nuclei present in the sample at that instant of time. Isn't it? According to radioactive decay law, the rate of decay of the radioactive substance at any instant is directly proportional to number of nuclei present in the sample at that instant of time. That's dN by dt directly proportional to what? N. Or we can write here dN by dt is equal to what? Minus lambda into N. dN by dt is equal to minus lambda into N. So what is lambda here? Constant, known as decay constant. Known as what? Decay constant. See here, negation indicates that nuclei present in the sample decreases with the time. See, negative sign. That is, as the time passes, number of nuclei sample what? Decreases with time. Got it here? Here, lambda is the constant known as what? Characteristic constant. It is called decay constant. It is characteristic constant. What is called by name characteristic constant? It is not possible to change by changing temperature, changing density, changing pressure, etc. It is constant for a given radioactive substance. That is radioactive decay law. Next, activity of radioactive substance at any instant is given by magnitude of rate of decay. Magnitude of rate of decay. That is magnitude of minus lambda into n means lambda into n. It is called the activity of radioactive decay. That is activity of radioactivity, means activity of a radioactive substance at any instant is directly proportional to what? Number of the nuclei present in the sample at that instant of time, directly proportional to. Why? Once again, lambda is constant here, called as what? Decay constant. Got it, students? In SS system, unit used to measure activity is what? Becquerel. But practically, we use the unit known as what? Curie, for sake of scientist name Marie Curie. Got it? Now, see, here as the time passes, I think, number of nuclei present in sample what decreases. How it decreases? According to the formula, n is equal to n naught into e to the power of minus lambda into t. That is, nuclei present in the radioactive substance decreases exponentially with the time. Got it? Decreases what? Exponentially with the time. See, according to formula, n is equal to n naught e to the power of minus lambda into t, where n naught is constant, known as what? Initial number of nuclei present in the sample. That is when time t is equal to 0. We can say here parent nuclei, number of parent nuclei. Got it here? Here n stands for daughter nuclei, n naught is nothing but parent nuclei. According to this formula here, that nuclei present in the sample what decreases exponentially with the time, as if plot the graph of variation of number of nuclei present in the sample along the y-axis, time along the x-axis. So graph is given by, see, exponentially decreases with what? Time. It is about this one. Next, we know, students, so far studied that when the nucleus of radioactive element emits alpha particle and beta particle, there is a change in mass number as well as change in what? Atomic numbers. So it forms new element known as what? Daughter element. During the formation from daughter element to, parent element to daughter element, every loss of cell should be what? Conserved. Got it? Every loss of should be what? Conserved. See, here that is, when the nucleus of radioactive elements emits m number of alpha particles and n number of beta particle, when a radioactive nucleus emits one alpha particle, newly formed element has mass number less by 4. When the nucleus of radioactive element emits 2 alpha particles, then decrease in mass number by what? 8. 3 alpha particle, decrease in mass number by 12. Isn't it? M alpha particle, decrease in mass number by minus 4m. Therefore, but there is no change in mass number when element emits what? Beta particles. That is, beta particle do not play any role on mass number. Therefore, if radioactive element emits m alpha particle and n beta particle, the newly formed element has the mass number a dash equal to what? A minus 4m. Got it? But atomic number changes, both because of the emission of alpha particle and beta particles. See, when the nucleus of radioactive element emits 1 alpha particle, decrease in atomic number by 2. 2 alpha particle, decrease in atomic number by 4. 3 alpha particle, decrease in atomic number by 6. M alpha particle, decrease in atomic number by Z minus 2m. Similarly, if 1 beta particle is emitted, increase in atomic number by 1. 2 beta particle is emitted, increase in atomic number by 2, isn't it? 3 beta particles, increase in atomic number by 3. N beta particle, increase in atomic number by n. Therefore, Z dash equal to what? Z minus 2m plus n. Z minus 2m plus n. Correct? It is what? Atomic number of the final element. It is the mass number of what? Final element. Correct? It is about what, students? Beta decay, alpha decay, gamma decay. Got it? Now we know, according to the radioactive decay law, number of nuclei present in the sample decreases exponentially with the time. We know it is the what? Variations of the n with what? Time. It is what? Number of nuclei in the sample when time t is equal to 0. See, from this curve, it clears that nuclei present in the sample reduces to 0 when t is equal to what? Infinite. It means that lifetime of the radioactive substance is infinitely long. That is, radioactive substance take infinite long time to disintegrate completely. Therefore, we can't define total lifetime of a radioactive substance. We can define only what? Half-life. So what is half-life? Total time taken by this radioactive substance to reduce half of its initial number of nuclei. That is nothing but what? Half-life. Got it here? See, so what is half-life? It is after one half-life. We know, I think, the nuclei present in sample reduces to what? Half of the number of the nuclei present in the sample. See, after one half-life, so nuclei present in sample reduces to what? Half of the initial number of nuclei. N is equal to N0 divided by 2. After 2 half-life, N0 by 4. After 3 half-life, N0 by 8. Isn't it? After 4 half-life, N0 by 16. It means that after N half-life, number of nuclei present in the sample reduces to what? N is equal to N0 divided by 2 to the power of N. See, or N by N0 is equal to 1 by 2 to the power of N. 1 by 2 to the power of what? N. Got it here? It is about what? See here, N, number of nuclei after N half-lives. Or activity after N half-life. M, mass of the sample after N half-life. Here, N0, R0 and M0 are what? Initial number of nuclei, initial activity, initial mass. That is, N by N0, R by R0, M by M0 is equal to 1 divided by 2 to the power of what? N. 1 by 2 to the power of N. It is very important formula, especially for what? Competitive examination students. Now see, half-life of radioactive sample depends upon what? Decay constant. That is, lifetime depends upon the decay constant. If decay constant is more, it disintegrates at the fast rate. As it disintegrates the fast rate, ಬೇಗ ಸಾಯ್ತದೆ ಅದು. ಬೇಗ ಸಾಯ್ತಾ ಹೋದರೆ ಅದರ ಲೈಫ್-ಟೈಮ್ ಏನಾಗುತ್ತೆ ಮಕ್ಕಳೇ? ಕಡಿಮೆ ಆಗ್ತದೆ. Isn't it? Therefore, see, half-life of radioactive substance is given by T is equal to 0.693 divided by lambda. What is lambda here? Decay constant. It means that half-life of the radioactive substance is inversely proportional to what? Decay constant. Inversely proportional to what? Decay constant. It is about what? Relationship between half-life and decay constant. Now I am going to discuss what mean life. We know, consider a sample consisting of different type of the nuclei. For example, assume there is a mixture of what? Radio nitrogen, radium-226, etc. So what is lifetime of the radio nitro? It is artificial radioactive isotopes, 11.3 minutes. So lifetime of, that is half-life of the radium-226 is, we know, 1620 years. 226 is what? 1620 years. 1620 years. See, if you test the mixture of radio nitrogen, radium, etc. Sorry, radio nitrogen and radium-226. See, one dies quickly, 11.3 minutes. Another take 1620 years to reduce half of its initial value. Then it is not possible to discuss lifetime of this such a mixture of sample by using our statistical law, students, isn't it? In order to overcome this difficulty, we define the what? Mean life. So what is mean life? Mean life of radioactive substance can be defined as the ratio of the sum of the lifetimes of all the individual nuclei to the number of the nuclei present in the sample. Correct here? Therefore, mean life of radioactive substance is measured by what? Reciprocal of the decay constant. I think it is about our synopsis. Now I am going to discuss what? Discussion part of the paper. Correct ಬರ್ತಾ ಉಂಟಲ್ಲ? ತೊಂದರೆ ಆಯ್ತು, ಬಂದಿಲ್ಲಲ್ಲ? ಕರೆಕ್ಟ್ ಬರ್ತಾ ಉಂಟಲ್ಲ ಈಗ? ತೊಂದರೆ ಇಲ್ಲಲ್ಲ ಅಂಥದ್ದು? ಇದು ವಾಯ್ಸಲ್ಲಿ ಕರೆಕ್ಟ್ ಇದೆಯಲ್ಲ? ಕರೆಕ್ಟ್ ಇದೆಯಲ್ಲ? ಬ್ರೇಕ್ ಬೇಡ, ಕೇಳಿದ್ದೀನಿ ಕರೆಕ್ಟ್ ಬರ್ತಾ ಉಂಟು ಏನಂತ. ಬ್ರೇಕ್ ಬೇಡ ನನಗೆ, ಅಂದೇನಾದ್ರು ತೊಂದರೆ ಆದರೆ ಕರೆಕ್ಟ್ ಇದೆಯಲ್ಲ? ವಾಯ್ಸ್ ಕರೆಕ್ಟ್ ಇದೆ, ಸೌಂಡ್ ಕರೆಕ್ಟ್ ಇದೆ, ಓಕೆ ಕಂಟಿನ್ಯೂ ಮಾಡ್ಬೋದಲ್ಲ? ಬ್ರೇಕ್ ಬೇಡ ನನಗೆ, ಆಯಿತಾ? ಹಾಂ, ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀರಾ? ಚೂರು ಕುಡ್ಕೊಂಡು ಹೋಗ್ತೆ ಆಗಿದ್ದೆ. ನಂದು ಏನಾದ್ರು ಮಿಸ್ಟೇಕ್ಸ್ ಇದ್ದರೆ ಸ್ಟಾರ್ಟಿಂಗಲ್ಲೇ ಬಿಗಿನಿಂಗ್, ಈಗ ನಾನು ಸಿನಾಪ್ಸಿಸ್ ಮುಗೀತು, ಗೊತ್ತಾಯ್ತಾ? ಈಗ ಮಾಡ್ತೀನಿ. ಇದೀಗ ನಾವು ಹೊರಗಡೆ ಬಂದ್ರಿಂದ ಪ್ರಾಬ್ಲಮ್ ಏನಾಗಿಲ್ಲಲ್ಲ, ಅಷ್ಟೇ ಅಲ್ಲ. ನನಗಂದರೆ ಇದು ವಾಯ್ಸ್ ಬಗ್ಗೆ ಸಮಸ್ಯೆ. ಆನ್ ಆಗಿದೆಯಾ? ಆನ್ ಉಂಟಲ್ಲ, ಇದು ಉಂಟಲ್ಲ, ಆನ್ ಉಂಟಲ್ಲ. ನನಗೆ ಆಗಳಿಂದ ಅದೊಂದು ಕನ್ಫ್ಯೂಷನ್ ಆಗ್ತಿತ್ತು, ಆನ್ ಇದೆಯಾ ಆಫ್ ಇದೆಯಾ ಅಂತ. ಸೌಂಡ್ ಆನ್ ಉಂಟಲ್ಲ, ಸರಿ. ಇದೆಲ್ಲ ಕರೆಕ್ಟ್ ಉಂಟಲ್ಲ, ಫೋಕಸಿಂಗ್ ಎಲ್ಲ ಕರೆಕ್ಟ್ ಉಂಟು, ಏನು ತೊಂದರೆ ಇಲ್ಲ. ಓಕೆ, ಯಾಕಂದ್ರೆ ಇಲ್ಲಿ ಮಾಡೋದು ಫಸ್ಟ್ ಟೈಮ್ ನಾನು. ಹಾಂ, ನೀವು ಪುನಃ ಹಂಗಿರುತ್ತೆ ಥಮ್ಸ್ ಅಪ್ ಕೊಡಿ. ಅದು ನನಗಿದು ಆಫ್ ಉಂಟು ಅನಿಸ್ತಾ ಇತ್ತು, ಅದಕ್ಕೆ. Okay, now I'm going to discuss, students, discussion part of our paper. First question: 3 radioactive substances have their activity in the ratio 1:4:6. The substances are heated to double their temperature, then activities will be. We know while discussing synopsis, I have discussed that activity of the radioactive substance is given by R is equal to what? Lambda into N. So what is lambda here? Decay constant. Constant for a given radioactive substance, isn't it? Therefore, it is not possible to change by externally. It is constant for a what? A given radioactive substance. Therefore, activity of radioactive substance at any instant is directly proportional to the number of the nuclei present in the sample at that instant of time. That is R directly proportional to what? N. We know R depends only on what? That is activity at any instant is depends on number of the nuclei present in sample at that instant of time. It does not depends upon other things. Therefore, it is not possible to change activity by changing what? Temperature. Therefore, even if you double the temperature or triple the temperature, or if you increase the temperature 4 times or any time, there is no change in what? It's activity. Therefore, still activity is in the ratio what? 1:4:6. Got it? That is R independent on, that is activity R independent on temperature. R is independent on temperature. Got it? It is not depends upon what? Temperature. So I hope all of you understood this question. Therefore, good answer is what? 1:4:6. A temperature does not change. It remains what? Constant. It is about first question. Okay. Now second one. In the process of nuclear fission. In the process of nuclear fission. We know what is nuclear fission. The phenomenon of splitting of a heavy nucleus into 2 light nuclei with release of energy. So we know, students, according to the binding energy curve, according to what? Binding energy curve. So what is binding energy curve? Specific binding energy taken along what? See, specific binding energy taken along what? Y-axis. That is binding energy per nucleus is taken along Y-axis. Mass number is taken along what? X-axis. This is the graph. So what is shape of the graph? So graph is given like this. Is the what? Shape of the graph. Got it? Near it is what we know. I think we studied about very well. So 30. What about here? 170. See, the specific binding energy of light nuclear low, so unstable. Heavy nuclear low, so unstable. Because of the instability of the heavy nucleus, it splits into 2 or more light nuclei. As the nuclei split into light nuclei, it is called fission. So resulting fragments are moved towards what? Intermediate regions. As the mass number decreases in our binding energy curve, the resulting element move towards the intermediate region. As it moves towards the intermediate region means more specific binding energy regions, isn't it? Therefore, that is due to nuclear fission, light nuclei splits, heavy nucleus splits into light nuclei. So as mass number decreases, binding energy per nucleon is what? Increases. Binding energy per nucleon is what? Increases. Therefore, due to nuclear fission, binding energy per nucleon is what? Increases. It is the answers. As well as due to nuclear fusion also. See, when two light nuclei fuse together to form a heavy nucleus, it moves towards what? Intermediate regions. Isn't it? That is both due to fusion and fission, resulting nuclear move towards what? Intermediate region. Therefore, by this graph, binding energy per nucleon is what? Increases. Therefore, good answer, binding energy per nucleon is what? Increases. Increases. Next question, students. Radioactive substance of mass 16 milligram reduces to 1 milligram after. We know after n half-lives. We studied, isn't it? After n half-lives. After n half-lives. Mass of the nucleus remains unchanged. Is given by m is equal to m naught divided by 2 to the power of n. M is equal to m naught by 2 to the power of n. Here what is n here? Number of half-lives. We know after 1 half-life, m is equal to m naught by 2. After 2 half-life, m is equal to half of the half. That is m naught by 4. M naught by 2 to the 4 of 2. After 3 half-life, half of the 1 by 4. M naught by 1 by 8. That is m naught by 2 to the power of what? N. Correct here. See, m is equal to m naught. A radioactive substance of mass 16 milligram reduces to 1 milligram after. See, 1 is equal to 16 divided by 2 to the power of n. This implies 2 to the power of n is equal to what? 16. Therefore, n is equal to 4. That is, number of half-life is given by 4. Therefore, good answer is what? 4 half-lives. 16 milligram reduces to 1 milligram after 4 half-lives. Therefore, good answer is what? D. D is the correct one. Got it? D is the what? Correct ones. Now, fourth question, students. Very good questions. See what is given here? A radioactive material at a given instant emits 90 particles per second. After 5 minutes, it emits 4.5 particle per second. Got it? Then its decay constant is. So what is asked here? A radioactive material at a given instant emits 90 particle per second. After 5 minutes, it emits 4.5 particle per second. Then its decay constant is. We know. See here, activity, that is emits means rate of emissions. Correct here. That is activity of the sample after the time t is given by r is equal to r naught e to the power of minus lambda into t. So r is given here 4.50. So 4.50 is equal to 90 e to the power of minus 5 lambda, because t is equal after 5 minutes. T is 5 minutes. Now 4.50 divided by 90 is given by 4.5 by 90. That's equal to what? 1 divided by 20. That is equal to what? E to the power of minus 5 lambda. Got it? E to the power of minus 5 lambda. See, 1 by 20 is equal to e to the power of minus 5 lambda means e to the power of 5 lambda is given by 20. So use logarithmic idea. That is 5 lambda is given by, take log, you know I think about logarithms. 5 lambda is equal to 2.303 log 20. Am I right? Yes. Isn't it? For example, if e to the power of x is equal to a, if e to the power of x is equal to a, then x is equal to what? Log a to the base e or ln a to the base e. Convert log to the base e to the log to the base 10. How can you do it? By multiplying 2.303, isn't it? Therefore, 5 lambda is equal to 2.303 log 20 to the base 10. No need to write 10, you know, I think. Now, we can write here 5 lambda is given by 5 lambda is equal to 2.303. 2.303. into log 20. What is the value of log 20, students? I think we know 1.3010 by using table. Okay. See, 5 lambda is given by nearly 2.303 into 1.3010. 2 into 1.5 is 3, but a 2.303, therefore nearly what? 3. Therefore, what is decay constant? Decay constant is given by 3 divided by 5. Decay constant is given by 3 divided by 5, students. So, what is 3 by 5? 0.6 per minute, isn't it? Therefore, decay constant is given by 0.6 per minute. 0.6 per minute. Therefore, good answer is what? D. D is the correct one. 0.6 per minute. Got it? Any doubt about this question? No. No, next one. See, atomic mass number of an element is 235 and its number is 92. The end product of this radioactive element is an isotope of lead having atomic mass number 203 and atomic number is 82. The number of alpha and beta particles emitted are. The number of alpha and beta particles emitted are. We are discussing synopsis. I am discussed. If a radioactive element emits a m number of alpha particles, decrease in mass number by minus 4m. No change in mass number because of emission of the beta particle, we know, according to beta decay. Isn't it? Let us consider, let m and n are, alpha and beta particles emitted by the nucleus. Okay, we know here mass number of the parent nucleus is what? 235. So 235 minus 4m is equal to what is given? Final mass number 203. Therefore, 235 minus 4m is equal to 203 means 235 minus 203 is equal to 4m. That is equal to what? 32. Got it? 32 is equal to 4m. This implies number of alpha particle is given by 8. So, m is equal to 8. Number of alpha particle is given by 8, students. See? So, in this answer, no need to calculate beta particle because in first option itself is given alpha is equal to 8. But in no any options, alpha is given 8. Therefore, correct one is 8. But chances will be there. Higu kodbadu alva. Alpha is equal to 8, beta equal to 6. Alpha is equal to 8, beta equal to 4. If there are more than one option involving alpha is equal to 8, you should calculate how many number of beta particles emitted. Isn't it? So, how can you find the number of beta particle emitted? No, very simple, we know. We already calculated in what? Alpha particle emitted. We know if there is a one alpha particle is emitted, decrease in atomic number by 2. M alpha particle is emitted, decrease in atomic number by minus 2m. Therefore, here, what is the atomic number of the parent nuclei? 92, isn't it? 92 minus 2m, that is what? 16. Plus n, here what is n here? Number of beta particle emitted. So, 92 minus 16 plus n is equal to final means atomic number of the parent nuclei, 82. See, 92 minus 16 is equal to what? 76. 76 minus n is equal to 8. This implies, what is the value of n? N is equal to 6. Isn't it? Sorry, 82. See, n is equal to 6. Isn't it? That is n is equal to 82 minus 76. That is n is equal to what? 6. So, correct answer is alpha is equal to 8 and beta is equal to 6. Therefore, it emits 8 alpha particle and 6 beta particles. 8 alpha particle, 6 beta particle. Any doubt? I hope all of you understood. Now go to next questions. See what is given here. Bit important question, students. May expect in NEET examination too. See, two radioactive samples initially contain equal number of radioactive atoms. N naught remains same here. Half-life of first element is 2 hours. And that of second is 1 hour. The ratio of activity of 2 sources after 4 hours. We know what is activity? Activity of the radioactive sample is given by R is equal to what? Lambda into N. That is R1 divided by R2 is given by R1 divided by R2 is equal to what? Lambda 1 by lambda 2 into N1 divided by N2. N1 by N2. So what is lambda 1 by lambda 2? T2 divided by T1 in terms of half-life. T2 by T1 into what? N1 divided by N2 students. We know half-life of the both the elements are given here. Half-life of the first one is 2 hours. T1 is given 2 hours. T2 is given 1 hour. No need to find T1 and T2. But we need N1 and N2. Since initially contain same number of nuclei, but half-life are different. After 4 hours, nuclei remains unchanged in two different substances are different. So we have to calculate N1 and N2. So what is N1 here? Nuclei present in the sample after 4 hours having a half-life of 2 hours. Got it? Nuclei present in the first sample after 4 hours having a half-life of what? 2 hours. We know after 4 hours means if half-life is 2 hours, after 4 hours means after how many half-lives? 2 half-lives. Therefore, N1 is given by N0 divided by 2 to the power of 2. That is N0 divided by 4. Similarly, what is N2 here? What about N2 here? N2 is given by after 4 hours having half-life 1 hour. After 4 hours means having half-life 1 hour. After 4 hours means after 4 half-lives. Therefore, N2 is equal to what, students? N0 divided by 2 to the power of 4. That is N0 divided by 16. N0 by what? 16. N2 is equal to N0 by 16. Now, come to the R1 by R2. Now, R1 by R2 is given by, what is R1 by R2? T2 by T1. T2 by T1. What is T2? 1 hour. T1, 2 hours. Isn't it? 1 by 2. T2 by T1, that is R1 by R2 is equal to T2 by 2, T1, that is 1 by 4, 1 by 2, into N1 by N2, N1 by N2, isn't it? What is N1 by N2? 1 by 4 by 1 by 16, 1 by 4 by 1 by 16, what is 1 by 4 by 1 by 16? 1 divided by 4 by 1 by 16, that is equal to what? 1 by 2 into 16 divided by 4, that is 16 divided by 8, that is equal to answer 2:1. Good answer is what? 2:1. Therefore, C is the right answers. Got it? Very good question, students. Remember. Okay. Any doubt about this question? No. Now I am going to next one. See, simple questions. 7th one. Half-life of radium is 1600 years. Half-life of radium is 1600 years. If the initial mass is 1 kg, what is the amount of radium left after 4008 years? See, what is given here? Half-life is given. See, half-life of the radium is given by 1600 years. 1600 years. Therefore, 4800 years is equal to how many half-lives? 4800 years is given by 3 half-lives. Isn't it? If 1 half-life is 1600 years, then 4800 years is equal to 3 half-lives. What is asked here? What is the amount of radium left after 4800 years? Means after 4800 years means after 3 half-lives. We know what is the amount of radium left means we know after n half-lives. After n half-lives, we have the formula. After n half-lives, amount of the substance is given by, in terms of mass is given by, m is equal to m0 divided by 2 to the power of n. Here n is equal to 3. Isn't it? N is equal to what? 3. Initial is 1 kg. M naught is 1 kg. Therefore, M is equal to 1 kg divided by 2 to the power of n. That is 1 divided by 2 to the power of 3. That is 1 divided by 8. Therefore, what is M? 0.125 kg, students. 0.125 kg amount of substance remaining undecayed after 3 half-life is given by 0.125 kg. It is about this one. So good one is what? B is the right answers. Any doubt? B is the correct one. Artha aitu. Okay, next question, students. Next one. Any doubt about this question? Okay, no any doubts. Next one. See, from an element X, there is emission of 1 alpha particle followed by 2 successive beta particles. The new element Y is. So what is given here? From an element X, there is emission of 1 alpha particle followed by 2 successive beta particle. The new element Y is. Okay, we know ZXA. Assume here ZXA. Emitter 1 alpha particles. So 1 alpha particles. So newly formed element has the atomic number less by 2, mass number say A is the chemical symbol, mass number say less by 4 because of the emission of what? 1 alpha particles. Followed by emission of 2 beta particles. Again it emits 2 beta particles. 2 beta particle. We know when a radioactive element emits 1 beta particle, increase in atomic number by 1. Here 2 beta particle, therefore increase in atomic number by 2. Z minus 2 plus 2. I am take the chemical symbol as say P. Okay, I am take the what? P. Because X, Y, Z. Because Z stands for what? Atomic number. So I am take this P. But there is no change in mass number because of the emission of the beta particle. No change in mass number. See, Z minus 2 plus 2, A minus 4. It is given by what? Z minus 2 plus 2, Z, P, A minus 4. See, newly formed element is given by, isn't it? Z minus 2 plus 2 means Z, P, A minus 4. See, X and P are having same atomic number but different mass numbers. X and P are having, isn't it? ZXA, ZP, A minus 4. X and P are having same atomic number, different mass number. If 2 or more nuclei having same atomic number, different mass number, then they called by name what? Isotopes. Isn't it? Then they called by name what? Isotope. Therefore, X and P are isotopes. X and P are what? Isotopes. Isn't it? That is the new element Y is, make it as P, okay. P. I taken Y as the intermediate one here, okay. So new element Y is an isotope of X. Therefore, new element Y is an, isotope of X. Isotope of X. Good one is isotope of X. B is the right one, it is not correct. Okay, an isotope of X. Correct here. X and P are what? Isotope of X. That's P is isotope of X. Good one is what? Isotope, not isotone. By mistake I did that one. Next one, students. So what is given here? Fraction that would remain after a time 1 by 2 is. That is, fraction that would remain after a time 1 by 2 is. Make a small correction in this question. Half-life of radioactive substance is. Half-life of radioactive substance is. Half-life of radioactive substance is. Half-life of radioactive substance is T. Full stop. Fraction that would remain after the time T by 2 is. Got it? Make a small correction in question. Half-life of a radioactive substance is t, fraction that would remain after a time t by 2 is, see, if half-life is t, after a time t by 2 means number of half-life is half, isn't it? Number of half-life is half. If half-life is t, after the time t by 2 means value of half-life is, number of half-life is what? Half. Therefore, number of half-life n is equal to what? Half. See, what is asked here? Fraction that would remain after a half-life. Fraction that would remain after a half-life. We know after n half-life. After n half-lives. After n half-lives, nuclear remains in the sample is given by n by n naught is equal to 1 by 2 to the power of n. That's given by what? 1 divided by 2 to the power of half. That is, fraction that would remain after half-life is given by 1 by root 2. Fraction that would remain after the time half-life is given by 1 divided by root 2. 1 divided by root 2. Good answer is what? A. A is the right one. A is what? Right answer, students. Therefore, good one is what? A. Any doubt? Simple formula. I think you used this formula 2-3 times in before questions, isn't it? Okay. No any doubt about these questions? Any doubt? Okay, next questions. See, good question now. Very good questions. So, what is given here? The counting rate observed from radioactive source at t is equal to 0 second was 1600 counts per second. The counting rate observed from radioactive source at t is equal to 0 second was 1600 counts per second. And at t is equal to 8 second, it was 100 counts per second. The counting rate observed at t is equal to 6 second will be. See, what is asked here? The counting rate observed from radioactive source at t is equal to 8 second was 1600. Initial activity is given by, say, R0 is equal to 1600 counts. And at t is equal to 8 second, assume here, let 8 is equal to 8 second is equal to 8 second is equal to n half-lives. N half-lives. 8 second is equal to, say, n half-lives. Got it? 8 second is given by n half-lives. N half-lives. 8 second is equal to n half-lives. Now we know R is equal to formula. R is equal to R0 divided by 2 to the power of n. It is after n half-lives. After n half-lives. So what is given here? After 8 second, 100. Therefore, 100 is equal to 1600 divided by 2 to the power of n. So 0, 0 get cancels. So 2 to the power of n is equal to what? 16. Therefore, n is equal to 4 half-lives. N is equal to what, student? 4 half-lives. We know that is 8 second is equal to 4 half-lives. 8 second is equal to 4 half-life. Hence, half-life is given by. So, what is half-life of radioactive substance? 8 second divided by 4. Half-life is equal to 8 by 4. That's equal to what? 2 seconds. The value of the half-life is what? 2 seconds. Value of the half-life is the 2 seconds. So, given here, the count rate observed at t is equal to 6 seconds will be. See, you know we got half-life is equal to 2 seconds. Therefore, 6 seconds is equal to how many half-life? 6 seconds is equal to 3 half-lives. Isn't it? 6 seconds is given by 3 half-lives. 6 seconds is equal to 3 half-lives. So, what is asked here? The count rate observed at t is equal to 6 seconds will be means count rate after 3 half-lives. So, count rate after 3 half-lives. So, R is equal to R0 divided by 2 to the power of n. That is, R is equal to R0. What is R0 here? 1600 divided by 2 to the power of 3. That is 1600 divided by 8. Got it? 1600 by 8. So what is 1600 by 8? 200 counts per seconds. 200 counts per second. Good one is 200 counts. Any doubt? Very good question. What is asked? The counting rate observed from radiator source at t is equal to 0 second was 1600 counts per second, and at t equal to 8 second it was 100, means reduces. Therefore 100 is equal to 1600 by 2n. So 2 to the power of n is equal to 16. So n is equal to what? 4. That is 8 second is equal to 4 half-life. So 1 half-life is given by 8 by 4. That is 2 second. Now 6 second means 3 half-lives. Same formula, again same formula, r equal to r naught by 2 to the power of n. That is 1600 by 2 to the power of 3. 1600 by 8, that's equal to what? 200. Therefore, count rate observed at the end of 6 second was 200 counts per second. Good one, 200 counts per second. Any doubt? Good question, students. Now, next question, see, conceptual based question. When the number of nucleons in nuclei increases, the binding energy per nucleon. So, easiest one, isn't it? First level questions. See here, we already studied binding energy curve. So, what is binding energy curve? Curve obtained by, means graph obtained by plotting the specific binding energy with what? Mass number A. So what we observed according to this graph here, that increases, it is maximum for A is equal to 56 and so on, decreases like this. It is about what? Binding energy curve. See, for element A is equal to 56, that's called Ferrous 56 maximum, we know. See, from this curve it clears that as mass number increases, nuclei increases means our question. When the number of nucleons in nuclei increases, the binding energy per nucleon, isn't it? The binding energy per, as you increase the number of nucleon, means as you increase the mass number, what are nucleus, students? Protons and neutrons. As nucleus increases, mass number increases. Because what is mass number? Sum of the protons and the neutrons. Isn't it? Sum of the protons and the neutrons. Therefore, as the mass number increases, in beginning, binding energy per nucleon increases. As mass number increases, in beginning increases, becomes maximum and decreases, isn't it? Therefore, first increases and then decreases with increase of mass number. See, in beginning, as A increases, binding energy per nucleon increases, becomes maximum. For A is equal to what? 56. That is for which one here? Ferrous 56. Isn't it? Ferrous 56, it is maximum. Ferrous 56, it is what? Maximum. Beyond that, what? Decreases. Somewhat up to 170, decrease of binding energy per nucleus is less. Beyond that, you know, I think instability, isn't it? Unstable nucleus. Therefore, good answer. First increases and then decreases with increase of mass number. Therefore, good answer is what? D. Any doubt? First increases and then decreases. First increases and then decreases. Okay, I'm going to next question, 12th one. See, a simple question. A freshly prepared radioactive source of half-life 2 hours emits radiation of intensity which is 64 times the permissible safe level. The minimum time after which it would be possible to work safely with this source is. Initially, intensity is what? 64 times the permissible level, students. We have to wait till its intensity reduces to what? 64 times. It is not possible to work with initial intensity because given there 64 times the permissible level means it is not possible to work with that, with fresh nuclei. We have to wait till its intensity reduces to 64 times. 64 times. See what is given here? Half-life is given. Find here. After how much half-life? Its activity reduces to 64. Stay. That is, we know, I think, formula R is equal to what? R naught divided by 2 to the power of n. What is n here? Number of half-lives. After which R naught reduces to R. R naught reduces to R. That is R by R naught. R by R naught is given by 1 divided by 64. That is equal to what? 1 divided by 2 to the power of n. So 2 to the power of n is equal to what, student? 64. 2 to the power of n is equal to what? 64. 2 to the power of 1 is equal to what? 64. To the power of n is equal to what? 64. Got it here? This implies n is equal to what? 6. That is number of half-life is given by 6. 6 is the number of half-lives. So we have to wait till 6 half-lives. 1 half-life is given 2 hours. 6 half-life is 6 into 2. Isn't it? By using formula. Time t is equal to n into t. Therefore, we have to wait till 6 into half-life, 2 hours. Therefore, t is equal to 12 hours. After what time safe to work? After 12 hours. Got it? After 12 hours. Option is what? B. Good question, students. Very good one. Any doubt? No any doubts. Next question. I am going to next one. See, simple questions here. The equation zxa transforms to z minus 1 ya plus 1 positron. Plus 1 positron. So, what is this decay? See, zxa, students, z is the atomic number. Atomic number decreases by 1 means proton number decreases by 1. The general is that zxa means decreases by 1 means before that. See, here zxa means atomic number decreases by 1 means proton convert into what, students? Neutron. Proton convert into what? Neutron. Plus 1 positron. Plus 1 water positron. Plus 1 positron. Again we know one more particle is emitted. It is called what? Neutrino. It is what? Standard equations. It is what? Standard equation. Positron. So positron, antiparticle of the electron, positron. That is what? Beta plus. That is called positive beta particle. It is nothing but what? Beta plus. Positive beta particle. That is called positron. That is what? Positron. It is antiparticle of what? Electron. It is also known as what? Positrons. That is positive beta particle. Therefore, that is nothing but what? Beta plus decay means positive beta decay. Therefore, good done is what? Positive beta decay. Remember, it is our simple. Simple question, students. Simple. Because there is no change in mass number. There is no change in mass number. Only change in atomic number means that is what? Beta decay. Check whether the atomic number increases by 1, negative beta particle. That is emission of electron. If atomic number decreases by 1, positive beta decay. That is atomic number decreases by 1 means positive beta decay. That is positron. Emission of positron. Any doubt? Therefore, good answer is what? Beta plus. Beta plus. Next question, students. So, what is given here? The binding energy per nucleon for deuteron and helium are 1.1 mega electron volt and 7 mega electron volt respectively. The energy released when 2 deuterons fuse to form a helium nucleus is. So we know 2 deuterons fuse to form a helium nucleus. Type of what? Somewhat fusion reactions. Energetically not possible. It requires external energy, you know. By law of conservation of energy, how much energy required to fuse to light nuclei? Same amount of energy was liberated. Isn't it? See here, the binding energy per nucleon for deuteron and helium are 1 per nucleon. Therefore, binding energy of deuteron is given by, first you find here, what is the binding energy of deuteron? Deuteron is nothing but what? 1H2. It is consisting of what? 2 nucleons. Per nucleon is given 1.1. Therefore, consisting of 2 nucleon, therefore 1.1 into what? 2. Got it? 1.1 into what? 2. 1.1 into what? 2. Got it? 1.1 into 2, that's equal to what? 2.2 mega electron volt. Next, binding energy of helium nucleus is 2He4. Binding energy of helium nucleus. Per nucleon is given 7, therefore 7 into 4, that is equal to what? 28 mega electron volt. So what is given here? The energy released when 2 deuterons fuse to form a helium nucleus is. So energy released E is equal to, so energy released is given by, energy released is given by, I think Q value, isn't it? So energy released Q is given by, or E is given by what? E is equal to, when 2 deuterons fuse to form a helium nucleus, that is 28 minus 2 into 2.2. 28 minus 2 into 2.2. That is 28 minus 2.2, 4.4 mega electron volt. So what is 28 minus 4.4? I think 6, 23.6. 23.6 mega electron volt. So good answer is 23.6 mega electron volt. 23.6 mega electron volt. It is the correct one. Any doubt? See, first you find what is the binding energy of deuteron and helium nucleus by using given data. Next given here, 2 deuterons fuse to form a helium nucleus. Therefore, helium nucleus binding energy 28, total energy minus 2 into 2.2. We will get 23.6 mega electron volt. I hope all of you understood. Go to next questions. So what is given, student, here? Simple question. A radioactive substance contains 10,000 nuclei and its half-life period is 20 days. The number of nuclei present at the end of 10 days is, see, half-life is given 20 days. So half-life is given 20 days. Therefore 10 days equal to what? 10 days equal to what? Half of half-life. Isn't it? Half of half-life. That is number of half-life. N is equal to what? Half. 10 days means half of half-life. Got it here? Number of half-life is given by half. The number of nuclei present, we know number of nuclei present after n half-life. N is equal to n naught by 2 to the power of n. That is equal to 10,000 divided by 2 to the power of half. So what is 2 to the power of half? Square root of 2. 10,000 divided by 1.414. So what is the value of 1. Square root of 2? 1.414. What is value of 1 by 1.414? 0.707. That is what? 0.707. 0.707 into 10,000. That's equal to, students, 7,070. Isn't it? That is 0.707. 7,070. 7,070. Therefore, number of nuclei remains undecayed after 10 days is given by 7,070. Very good question. Simple one. Simple one. Okay, I hope all of you understood. Go to next one. 16th question. See, very good questions. So what is given here? After 280 days, the activity of a radioactive sample is 6,000 disintegration per second. DPS stands for disintegration per second. The activity reduces to 3,000 DPS after another 140 days. The initial activity of sample in DPS is, see, the activity reduces to 3,000 DPS after another 140 days. Here given 6,000 reduces to 3,000 in 140 days is nothing but half-life is equal to 140 days. Isn't it? 6,000 DPS. 6000 disintegration per second reduces to 3000 disintegration per second in 140 days given here, means that, see, 6 reduces to 3 means that half-life T of is equal to what? 140 days. Got it? Especially half-life represented by the T half, but in our NCR textbook given capital letter T as half-life. But standard notation T half, but in NCR given capital letter T, I used here T half. See, 6000 reduces to 3000 DPS in 140 days. It means that half-life is 140 days. Half-life is 140 days. Therefore, see, after 280 days, the activity of radioactive sample is 6000 DPS. What is asked here? The initial activity of the sample is, after 280 days, 6000 means after 2 half-life 6000. Isn't it, students? See, 1 half-life is 140 days. Therefore, 280 days equal to, so what is meant by 280 days? 2 half-lives. 2 half-lives. After 280 days, 6000, initial activity means before 280 days, means before 2 half-lives. Now, before 2 half-lives, before 2 half-lives, activity is given by formula R naught. We know R is equal to R naught by 2 to the power of n. R naught is equal to what? 2 to the power of n into R, isn't it? See, before 2 half-lives, R is given by formula 2 to the power of 2. Sorry, R naught is given by 2 to the power of 2 into what? R. By using formula 2 to the power of n. Using which formula? Using, remember, R by R naught is equal to 1 by 2 to the power of n, or R is equal to R into n square, or n square into R. See, R naught is given by R, that is 6000, into 2 square, that is 4. 6000 into 2 square, 6000 into 4, that is what? 24,000 disintegration per second, students. Any doubt? 24,000 disintegration per second. That is the answers. Any doubt here? Simple one. 6000 reduces to 3000 after 140 days. Therefore, half-life is 140. Initial activity means after 280 days given 6000 means before 280 days, before 2 half-lives. Formula before 2 half-lives. R naught is given by R into n square. R into what? Isn't it? R into n square. What is n here? Number of half-lives. Got it here? See here, R naught, R 6000 equal to 2 square. Here number of half-life is 2. Therefore, 24,000, 600,000 into 2 square, 24,000 disintegration per second. Any doubt? I hope all of you understood. Good question, this one. I am going to know 17th question, students. 17th one. See, a radioactive material decays by simultaneous emission of 2 particles with respect to half-lives 1620 year and 810 year. The time after which 1/4 of material remains undecayed is 1/4 of the material remains undecayed is undecayed means after 1/4 means after 2 half-lives. So first you find what is the half-life of combined decay. See, a radioactive material decays by simultaneous emission of 2 particles with respect to half-life 1620 year and 810 year. We know lambda for combined decay, decay constant for combined decay, decay constant for combined decay, students. Lambda is given by lambda 1 plus lambda 2. That is how in terms of half life 1 by T is equal to 1 by T1 plus 1 by T2. That's given by 1 by T1 1 by 1620 plus 1 by 810. Take common denominator. What? Take common denominator 1620, that is 3 divided by 1620. Got it here? That is 1620. So 2, 2, 1. So 3 by 1620. It is 1 by T. That is what? 1 divided by 15, 5, 1500, 120. So 40. So 540. So half-life is given by half-life of combined decay. Half-life of combined decay. T is given by 540 days. Got it? T is equal to what? 540 days. T is equal to 540 days. Got it? It is what? Half-life of the combined decay. Here what is as the time after which 1/4 of material remains undecayed is 1/4 of material remains undecayed. ಉಳ್ಕೊಂಡಿದ್ದು. That is after n half-life, how much amount of material undecayed? That is given by R by R naught is equal to 1 by 2 to the power of n. Isn't it? That is 1 divided by 4 is equal to 1 divided by 4 is equal to 1 divided by 4 is given by 1 by 4 is equal to what? 1 by 2 to the power of n. This implies n is equal to what? 2. That is n is equal to 2 means n is equal to 2 half-lives or half-lives. 2 half-lives. So we know 1 half-life is 540. Time after which 1 by 4th undecayed means after 2 half-life 1 by 4th is undecayed. So 1 half-life is 540 days. Therefore I will write here. Therefore T is given by n into T, number of half-life into 1 half-lives. There is 2 into 540. 2 into what? 540. So what is 2 into 540? 1080. Therefore, the time after which 1/4 of material is undecayed is what? 1080 years. 1080 years. Correct here? Good answer is what? 1080 years. T is equal to 1080 years. It is the answers. 1080 years. Therefore, good answer is what? 1080 years. It is the answers. Any doubt? Okay, continue to the next 18th questions. See what is given here. The number of parent atoms disintegrated in a time equal to the mean life is. The number of parent atoms disintegrated in a time equal to the mean life is. In a time equal to the mean life is. So what is given, student, here? Number of parent atom disintegrated. See, number of undecayed, undisintegrated is given by undisintegrated. How can you find here? Number of parent atom disintegrated. So undecayed. What is n here? Number of nuclear remains what? Undecayed. Isn't it? So using formula n is equal to what? n naught into e to the power of minus lambda into t. So undecayed number of nuclei, undecayed number of nuclei, undecayed after t is equal to tau. What is tau here? Known as mean life. Mean life. So we know what is mean life. Tau is given by mean life is equal to what? 1 by lambda. Therefore, number of nuclei undecayed after time mean life is n is equal to n naught into e to the power of minus lambda into t, minus lambda into 1 by lambda. That is n naught into e to the power of minus 1. Lambda, lambda get cancels. That is n naught divided by e, students. N naught by e. See, number of nuclei undecayed means undisintegrated. ಉಳಿದುಕೊಂಡಿದ್ದು after mean life ಎಷ್ಟು ಉಳಿದುಕೊಂಡಿದೆ? n naught by. ಇಲ್ಲಿ ಕೇಳಿದೆಷ್ಟು? ಎಷ್ಟು ಡಿಸಿಂಟರೇಟ್ ಆಗಿದೆ? How can you find it? ಎಷ್ಟು ಖಾಲಿಯಾಗಿದೆ? ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ 10 ಇದ್ದಿತ್ತು, 6 ಉಳ್ಕೊಂಡಿದೆ, ಖಾಲಿ ಆದಷ್ಟು ಯಾವಾಗ 10 - 6 4. ಸಿಮಿಲರ್ಲಿ ಇಷ್ಟು ಉಳ್ಕೊಂಡಿದೆ, ಇಷ್ಟು ಇದ್ದಿತ್ತು, ಅನ್ಡಿಕೇಟೆಡ್ ಸ್ಕ್ವೇರ್ ಬೈ ಡಿಸ್ಇಂಟಿಗ್ರೇಟೆಡ್, ಟೋಟಲ್ ನಂಬರ್ ಆಫ್ ನ್ಯೂಕ್ಲಿಯೈ ಡಿಸ್ಇಂಟಿಗ್ರೇಟೆಡ್, total number of nuclei disintegrated is equal to n0 minus n. ಇಷ್ಟಿತ್ತು, ಇಷ್ಟು ಉಳ್ಕೊಂಡಿದೆ, ಖಾಲಿಯದ್ದು n0 minus n. That's equal to what? n0 minus n0 by e. Take n0 outside, n0 into 1 minus 1 divided by e. n0 into 1 minus 1 by e. Therefore, good answer 1 minus 1 by e into n0. B is the right ones. That is 1 minus 1 by e into what? n0. So good one is what? Second option is correct one, students. Correct one is second options. Any doubt? I hope understood. Go to next question, 19th one. See, what is given here? The ratio of radii of nuclei of two atoms of elements of atomic mass numbers 27 and 64 is. The ratio of radii of nuclei of two atoms of elements of atomic mass numbers 27 and 64 is. We know radius of the nucleus of mass number A are directly proportional to what? Cube root of its mass number. That is R. So R1 divided by R2 is given by, what is the formula? A1 divided by A2 whole to the power of 1 divided by 3. So what is A1? 27. What is A2? 64. 27 by 64 whole to the power of 1 by 3. That's cube root of 27. 3 into 3 into 3, 27. Therefore 3. 4 into 4 into 4 into 4. It is what? 4. Therefore good answer is what? 3:4. Isn't it? So 3:4. So A is the right one. A is what? Correct choice. A is the right one. Therefore, that is what? 3:4. Therefore, radii are in the ratio 3:4. I hope you understood simple questions. Simple formula. Radius of the nucleus is directly proportional to what? Cube root of its mass number. Or directly proportional to e to the power of 1 by 3. Finally, we will get what? 3:4. Go to next one, 20th questions. See, conceptual based question, students. So, what is given here? A radioactive substance has an average life of 5 hours. A radioactive substance has an average life of 5 hours. In a time of 5 hours, so average life is not mean life, isn't it? Average life is not mean life. So what is mean life? Reciprocal of the decay constant, isn't it? That is mean life is given by tau is equal to reciprocal of decay constant. That is 1 divided by, what is decay constant? 0.693 divided by half life, isn't it? Therefore half life is given by 0.693 times mean life. Half life is equal to what? 0.693 times mean life. It means that mean life tau greater than half life, isn't it? What is T here? T stands for what? Half life. Mean life is greater than half life. Mean life is greater than half life, isn't it? See what is given here? See, mean life is greater than half life. For half life is less than mean life. That is half life of radioactive substance is 69.3 times the mean life. For example, if mean life of radioactive substance is 100 years, then half life is 69.3 years. 69.3 years. See here half life is less than mean life. Here asked here mean life is 5 hours. Means half life is less than 5 hours. In time 5 hours means in time more than half life. In time more than half life, more half of the number of nuclei undergo this, isn't it? In time more than half life, more half of the nuclei undergo disintegrations. Therefore, more half of the nuclei undergo disintegration. Therefore, more than half of the active nuclei decay. Got it, students here? See, half life is, that is half life is here less than, isn't it? Half-life is what? Less than 5 hours. Mean life greater than, mean life is less than, greater than half-life means here T less than 5 hours. Half-life is less than 5 hours. Asked in time 5 hours means in time greater than half-life. More than half of the active nuclei undergo what? Decay. Right answer is what? C. Right answer is C. Okay, students. I hope all of you understood this ones. Students, I am going to next question, 21st question. So what is in 21st question? A radioactive substance decays at the rate of 5000 disintegration per minute. Means activity 5000. After 5 minutes, it disintegrates at the rate of 1250 disintegration per minute. Then the decay constant is, very good question students, may ask in not NEET examinations. See here, activity at an instant is 5000, reduces to 1250 after 5 minutes, isn't it? Then decay constant is, we know, activity of the radioactive substance after a time t is given by R is equal to R naught into e to the power of minus lambda into t. See, after the time t reduces to 1250, initially how much? 5000. So after the time 5 minutes, therefore minus 5t. That is t is equal to 5 minutes. Sorry? See, after the time at 5 minutes, t is equal to 5 minutes, so 5 lambda. So 1250 is equal to 5000 e to the power of minus 5 lambda. So e to the power of minus 5 lambda is equal to what? 1 times 4 times 1 divided by 4. Take reciprocal. This implies e to the power of 5 lambda is equal to what? 4. I took reciprocal on both sides, so minus become plus. See here, e to the power of minus 5 lambda equal to 1 by 4. So e to the power of 5 lambda is equal to 4. What is asked here? Decay constant is asked. Find what is lambda. Use the rule, logarithmic rule. If e to the power of x is equal to a, x is equal to log e to x to the base e, isn't it? That's 5 lambda is equal to 5 lambda is equal to what? Ln 4. Again use one more rule here. See, ln 2 to the power of what? 2. Ln 2 to the power of 2. 5 lambda is equal to ln 2 to the, that is 4. We can add 4 as 2 to the power of 2. Again use one more rule here. Log m to the power n is given by n log m. Isn't it? So, lambda is given by, next lambda is equal to what? 5 lambda is equal to this one. So, 1 divided by 5. Here see, ln 2 to the base 2 means 2 into ln 2. So, what is 1 by 5? 0.2. 0.2 into 2 is what? 1 by 5 is what? 0.2. So, 0.2 into 2 is what? 0.4. Therefore, answer becomes what? 0.4 ln 2. 0.4 ln 2. Good answer is what? 0.4 ln 2 per minute. Got it here? See, lambda is equal to 1 by 5 into 2 into ln to the 2 means that is 1 by 5 is the 0.2. Therefore, 0.2 into 2 that is 0.4. 0.4 ln 2. Good answer is 0.4 ln 2 per minute. So, correct one is what? A. A is the right one. Any doubt? Simple questions, but very good questions. Remember. Okay, go to next one. I hope all of you understood this ones. Next question, students. 22nd one. So, what is given here? Very good question, this one. See, the half-life of a radioactive substance is 20 minutes. The half-life of the substance 20 minutes. The approximate time interval T2 minus T1 between the time T2 when 2 by 3 of it had decayed and time T1 1 by 3 of it had decayed. See, asked here, what is the time interval between What is the time interval between 1 by 3 of decade to 2 by 3 of decade? Isn't it? See, the half-life of substance is 20 minutes. The approximate time interval T2 minus T1 between the time T2 when 2 by 3 of it had decayed. 1 by 3 decay agide. 1 by 3 decay agide at the end of time T1. 1 by 3 decay agide anta helidre how much number of nuclei remains in the sample unchanged? 2 by 3. Isn't it? 2 by 3. See, here N1 is equal to, what is given here? N1 is given by what? 2 by 3 times N0. ಉಳ್ಕೊಂಡಿದ್ದು 2 by 3 times N0. Correct? See, the approximate time interval T2 minus T1 between the time T2 when 2 by 3 of it decayed. Nodi. And time T1 1 by 3 of it decayed. Correct here? 1 minus 1 by 3. What is 1 minus 1 by 3? 2 by 3 N0. See, at the end of time T2, how much number of nuclei remains undecayed? That is, at the end of time T1, 2 by 3 of undecayed. See, at the end of time T2, 2 by 3 of it decayed. How much number of nuclei remains in the sample? 1 by 3 times N0. Got it? ಇದು ಉಳಿದುಕೊಂಡಿದ್ದು. Remember, n is equal to n0 by 2 to the power of n means where n stands for number of nuclei remains unchanged. In equation, in formula, n is equal to n0 to the power of minus lambda into t, there n stands for number of nuclei remains unchanged after the time t second. Remember, after the time t. Here see n by n0. What is asked here? What is the time interval in which activity reduces from 2 by 3 to 1 by 3? What is the time interval? It is at the end of time T1 remains in the sample. At the end of time T2 remains in the sample. Here is asked what? What is the time T2 minus T1 means time interval during which nuclei present in the sample reduces from 2 by 3 to 1 by 3. 2 by 3 to 1 by 3. Let us assume here, let T2 minus T1 is n half-lives. Let T2 minus T1 is what? N half-life. We don't know what is the value of n because the half-life is given 20 minutes. Okay. Let T2 minus T1 is what? N half-lives. We know after n half-lives, n is equal to n0 by 2 to the power. What is n0 initially? Here n is equal to n0 by 2 to the power of n. What is final? N2. So n2 by n1 is equal to what? 1 divided by 2 to the power of n. So what is n2 by n1? 1 by 3 by 2 by 3. 1 by 3 by 2 by 3. What is 1 by 3 by 2 by 3? 1 by 3 into 3 by 2. That is 1 by 3 divided by 2 by 3. See, 3 get cancels. That's equal to 1 divided by 2. Isn't it? N2 by N1 is given by 1 by, we assumed here, T2 minus T1 is what? N half-life. So 1 by 2 to the power of n is equal to 1 by 2. This implies n is equal to what? 1 half-life. That is, here 2 by 3 reduces to 1 by 3 in time equal to 1 half-lives. Therefore, time is given by, therefore time T2 minus T1 is equal to T2 minus T1 is equal to, we assumed here n half-life. We got here T2 minus T1 is equal to what? 1 half-life. T1 minus T1 is equal to 1 half-life, 1 into T. That's equal to what? 1 into 20 minutes. 1 into 20 minutes, isn't it? Got it here. See, 1 into 20 minutes is nothing but what? 20 minutes. Therefore, time taken is 20 minutes. Therefore, time taken to reduce from N1 to N2 is 20 minutes. T2 minus T1 is given by 20 minutes. Any doubt? Very good question, students. See, very good question. See, here at the end of time T2 given here 1 by 3 undecayed. Isn't it? ಸೊ 2/3 ಅನ್ಡಿಕ್ ಬಿಕಾಸ್ ಇಯರ್ ಗಿವನ್ ಇಸ್ ಡಿಕೇಡ್. ಇಲ್ಲಿ ಕೊಟ್ಟಿದ್ದು ಡಿಕೆ ಆದದ್ದು, ಇಲ್ಲಿ 11 ಮತ್ತು 8 ಉಳಿದುಕೊಂಡಿದ್ದು. ಅಂದರೆ 2/3 ಡಿಕೆ ಆಯಿತು ಅಂತ ಹೇಳಿದ್ರೆ ಉಳ್ಕೊಂಡಿದ್ದೆಷ್ಟು 1/3. ಎಟ್ ದಿ ಎಂಡ್ ಆಫ್ T1 1/3 ಡಿಕೆ ಆಯಿತು ಅಂತ ಹೇಳಿದ್ರೆ ಉಳ್ಕೊಂಡಿದ್ದೆಷ್ಟು 2/3. ಗಾಟ್ ಇಟ್ ಹಿಯರ್? Okay, try to understand this one. So, very good question, this one. I hope all of you understood very well. Now, next question, students. I think I'm going to 23rd question now. See what is given here. In 23rd question, a radioactive sample S1 having the activity A1 has twice the number of nuclei as another sample of S2. What is given? A radioactive sample S1 having the activity A1 has twice the number of nuclei. That is N1 is equal to what? 2 times the N2. Twice the number of nuclei. If A2 is equal to 2A1, then the ratio of half-lives of S1 to that of S2 is. What is asked here? Ratio of the half-life. See, in terms of activities, say A1 by A2 is given by lambda 1 divided by lambda 2 into N1 divided by N2. So what is lambda 1 by lambda 2? T2 divided by T1 into N1 divided by N2. So what is asked here? See, because lambda inversely proportional to the decay constant. We know lambda is equal to 0.693 times half-life, isn't it? Therefore, lambda 1 by lambda 2 means T2 by T1. So what is asked here? T1 by T2 is equal to asked for T1 by T2. What is T1 by T2 here? T1 by T2 is given by what? A2 divided by A1. A2 divided by A1. A2 divided by A1 into what? Got it? So T1 by T2 is equal to A2 by A1 into what? N1 by N2. N1 divided by N2. N1 by N2. T1 by T2 is equal to N2 by cross multiplication. T1 by T2 is equal to what? Like this. Okay, A2 by A1 into N1 by N2. So what is A2 by A1? A2 given 2A1 2. A2 given 2A1. That is A2 by A1 equal to 2. N1 is given 2N2, so 2. That is 2 by 1 into 2 by 1. That's equal to what? 4. So 4 is to 1. Good answer is what? 4 is to 1. T1 by T2 is equal to 4 is to 1. Any doubt? T1 by T2 is equal to what? 4 is to 1. 4 is to 1. Correct answer is A. I hope all of you understood. Very well questions. Very good question, students. Okay, go to next question now. Go to next one. See, pick out the correct statement from the following conceptual based questions. Pick out the correct statement from the following. So what is given here? A answer, energy released per unit mass of reactant is less in case of nuclear fusion reaction. I told you, students. We are discussing synopsis. When four protons are fused together while forming a stable nucleus, how much change released? 26.7. Therefore, energy released per unit mass is given by 26.4 mega electron volt by 4. That's equal to what? Greater than 6 mega electron volt. It is the energy per fusion in nuclear, isn't it? Energy per nucleon in fusion. What about in case of fission? By the participation of the 235 plus 1, 236. How much are released? 200. Just 200 by 236, less than 1. Therefore, energy per unit mass is less in fission, more in fusion. Therefore, energy per unit mass is more in fusion, less in fission. But here given energy per unit mass of the reactant is less in fusion, therefore it is not correct. It is not correct. Packing fraction may be positive or may be negative. Correct, isn't it? We'll discuss in synopsis. I'm explaining this one. Packing fraction may be negative or may be positive. If nuclei having a negative packing fraction is more stable. Remember, Positive packing fraction is less 1. Therefore, correct one is what? B. What about third one? Plutonium-239 is not suitable for fission reaction. Remember students, 239, plutonium-239 is a good example for fissionable material. Good example for fissionable metal. Especially it is used in nuclear weapons. Remember students, especially this plutonium-239 is used in nuclear weapons. It is a good example for fissionable. But what is given here? Not suitable, therefore it is not correct. Because plutonium-239 is suitable for fusion, therefore it is wrong. Next, for stable nucleus, the specific binding energy is low, meaningless. For stable nucleus, specific binding energy is what? More. Therefore, A, C, D are not correct. Correct one is only what? B. Packing fraction may be negative or maybe what? Positive. Therefore, good one is what? B is the right one. I hope all of you understood. Now go to next one, 25th questions. So what is given here? See, the decay constant of radioisotope is lambda. If A1 and A2 are its activities at time T1 and T2 respectively, the number of nuclei which have decayed during the time T1 minus T2 is, make a small correction in the question in time T2 minus T1 students. Make a small question in time T2 minus T1 is. It is wrong. T2 minus T1 is. Make a small correction in question. In time T2 minus T1 is. Because T2 greater than T1. Okay. The decay constant of radioisotope is lambda. If A1 and A2 are activities at time T1 and T2. So what is A1? A1 is equal to what? Lambda into N1. A2 is equal to what? Lambda into N2. A2 is equal to what? Lambda into N2. See what is asked here? The number of nuclei which have decayed during the time. Here see, here lambda into N. This implies N1 is equal to what? A divided by lambda. That is at the end of time T1, number of nuclei remain in the sample. At the end of time T2, number of nuclei remain in the sample. N2 is equal to what? A by lambda. So what is asked here? N1 minus N2. So N1 minus N2, number of nuclei decayed. That is, A1, A2. So A1 by lambda, A2 by lambda. See, lambda remains common here. So 1 by lambda into A1 minus A2. It is the answers. Number of nuclei remains in this. Number of nuclei disintegrated in time T2 minus T1. Make a small corrections in question. Already told. Not T1 minus T2. T2 minus T1 is N1 minus N2 equal to 1 by lambda into A1 minus A2. Therefore, good answer is what? A1 minus A2 divided by lambda. A1 minus A2 divided by lambda. It is the what? Correct answers. I hope all of you are understood. Go to next one, I think 26th questions. See what is asked here in 26th question? A stationary radioactive nucleus of mass 210 units disintegrates into an alpha particle of mass 4 units and residual nucleus of mass 206 unit. If the kinetic energy of the alpha particle is E, then the kinetic energy of the residual nucleus is. See, we know kinetic energy. So we know what? Kinetic energy is given by Kannada Chalana Shakti. We know kinetic energy K is given by P square divided by 2m. What is P here? Momentum. Where P is equal to momentum remains constant, isn't it? Where P is equal to what? Momentum remains constant. Momentum remains what? Always constant. Because we studied, I think, momentum remains always conserved. Kinetic energy no need to be conserved, isn't it? See, K is equal to P square, that is kinetic momentum, that is kinetic energy K is inversely proportional to what? Mass. Because momentum is constant, therefore kinetic energy K is inversely proportional to mass. We know here mass of the alpha particle is, what is the mass of the alpha particle? 4 units. Mass of the residual nucleus is, say I am take the Rn notation, 206 unit. Mass of the alpha particle is 4 unit. Mass of the residual nucleus is what? 206 unit, students. What is asked here? If the kinetic energy of the alpha particle is E, then kinetic energy of the residual nucleus is. Kinetic energy of what? Residual nucleus is take kinetic energy of the residual nucleus divided by kinetic energy of the alpha particle is equal to, because kinetic energy inversely proportional to the mass, therefore mass of the alpha particle divided by mass of the residual nucleus. What is mass of the alpha particle? 4. What is mass of residual nucleus? 206. That is equal to what? 2 divided by 103. 2 divided by 103. Isn't it? That is, kinetic energy of the residual nucleus is given by, residual nucleus is equal to 2 divided by 103 times the kinetic energy of the alpha particle. Kinetic energy of residual nucleus is 2 divided by 103 times the kinetic energy of the alpha particle. What is given here? Kinetic energy of the alpha particle is E. Therefore, 2 divided by 3 times the water E. So, good answer. 2 by 103 times the water E. 2 by 103 times the E. It is about what? Answer is B. I hope all of you understood. See, here important to note that, right, expression for kinetic energy in terms of momentum, P square is there, because we studied that is in first PUC, kinetic energy of the body of mass m is given by E is equal to half m v square. That is in terms of mass and velocity. According to that formula, kinetic energy directly proportional to the mass. But here, expression in terms of square of the momentum remains. Sorry, square of the momentum, students. You take in terms of square of the momentum, P squared by 2m, isn't it? P squared by 2m. That's if two bodies are having equal momentum, then which one is having a more kinetic energy, having more momentum, isn't it? Very good question, this ones. I hope all of you understood. Now, next question, students. I think 27th one. See, two radioactive nuclei, A and B, have disintegration constants lambda A and lambda B, and initially Na and Nb number of nuclei of them are taken. That is, initial number of nuclei are same, different. Then the time after which their undissociated nuclei are same is, what is asked here? Two radioactive nuclei A and B have disintegration constants lambda A and lambda B, and initially Na and Nb number of nuclei of them are taken. Then the time after which their undisintegrated nuclei are same is, undisintegrated nuclei same. Asked here, after what time undisintegrated nuclei are same, isn't it? Correct here. So we know undisintegrated nuclei using formula, using number of nuclei remains unchanged after the time t second is given by n is equal to n naught into e to the power of minus lambda into t. N is equal to. See, here undesignated nuclei remains same. That is given here. What is given here? Na e to the power of minus two radioactive nuclei having A and B. Disintegration constant lambda A. Okay, lambda A into T, isn't it? Then time after which their undissociated nuclei are same. Lambda A into e to the power of minus T. That is Nb into e to the power of minus lambda B into T. I took care after the time T undesignated are same. That is Na into the power of minus, that is given here. Undesignated nuclei are same. That is N remains same here. After the time T. See, here Nb divided by Na. Nb divided by Na is equal to what? E to the power of Nb divided by Na is given by Nb divided by Na is given by e to the power of minus lambda A into T by e to the power of minus lambda B into T. Take reciprocal at in right hand side. minus will become plus, isn't it? That is e to the power of lambda b into t divided by e to the power of lambda a t. We know x to the power of m by x to the power of n, x to the power of m minus n. Therefore, e to the power of lambda b minus lambda a into what t. Asked here after what time, isn't it? That is lambda b minus lambda a into t is equal to what? Neperian logarithm nb divided by na, ln nb by na. Got it? Now ask at time t. What is time t here? Time t is given by 1 divided by lambda b. Just a minute. See here, 1 divided by lambda b minus lambda a into, isn't it? Lambda b minus lambda t is equal to this one. So it goes to what? Denominator. So 1 by lambda b into lambda into what? Ln of nb divided by na students. 1 by lambda b minus lambda a into ln of nb divided by na. So good answer is what? C. Got it here? 1 by lambda b minus lambda a ln of nb divided by na. Therefore, very good questions. Correct here. So good one is what? C is the right one. Any doubt? Simple. Given here, undissociated nuclei remain same, but initially they are different too. Asked after what time? I am assumed here after the time t. After the time t. See, after the time t. Good answer. 1 by lambda b minus lambda a ln of nb divided by na. I hope all of you understood. Now go to next one, 28th questions. See, once again, very good questions. See, two radioactive materials X1 and X2 have decay constants 10 lambda and lambda respectively. Means rate of decay different. If initially they have the same number of nuclei, then the ratio of the number of nuclei of X1 to that of X2 will be 1 by E after a time. What is given here? Initially they have the same number of nuclei. That is given by X1 is equal to what? Say N0 into e to the power of minus 10 lambda t. Okay, given 10 lambda. Again, X2 is given by, because initially they contain same number of nuclei, minus 10 into, I think, lambda, isn't it? 10 lambda and lambda. So, e to the power of minus lambda into t. So, what is asked here? What is asked here? After what time ratio of x1 to x2 is 1 by e, isn't it? That is, x1 divided by x2 is equal to what? What is x1 divided by x2? E to the power of minus 10 lambda t, n0 get cancels, minus 10 lambda t divided by e to the power of minus lambda t. That is given by, take reciprocals. It goes to what? Minus 10 lambda t, it goes to plus, minus 10 plus 1, minus 9 lambda t. E to the power of what? Minus 9 lambda t. Got it? What is e to the power of minus 9 lambda t? E to the power of 1 by e to the power of what? 9 lambda t. Minus become plus. 1 by e to the power of 9 lambda t. Got it here? It goes to numerator, means become plus, minus 10 lambda t plus lambda t minus 9 lambda. 1 by e to the power of 9 lambda t. Now look at the question. What is asked? The ratio of the number of nuclei x1 to x2 will be 1 by e after a time t. Will be 1 by e after a time t. Given here, x1 by x2 equal to 1 by e. That is, 1 by e to the power of 9 lambda t is equal to 1 divided by e. Therefore, it is 1 by e. That is, from these two we got e to the power of 9 lambda t is equal to e, means this implies 9 lambda t is equal to what, student? 1. 9 lambda t is equal to what? 1 by e to the power of 9 lambda t is equal to e to the power of 1. Therefore, 9 lambda t is equal to, we got 1. Therefore, time t is given by, what is time t? 1 by 9 lambda. 1 divided by 9 lambda. Good answer. 1 divided by 9 lambda. D is the right options. Isn't it? D is what? Correct. Any doubt? Give one simple question. Initially they contain same number, take ratio. We will get what? E to the power of minus 9 lambda, take reciprocal, minus become plus 1 by 9 lambda t. Here see, e to the power of 9 lambda t is equal to e to the power of 1. So we got 9 lambda t is equal to 1. Equate on both sides. Equate. So 9 lambda t is equal to 1 means t is equal to 1 by 9 lambda. So good answer is what? D is the right one. D is the correct one. I hope all of you understood. Now next question, 29th one. See. So what is given student here? Two identical samples, same material and same amount. Same material means having same decay constant. Same amount, P and Q of a radioactive substance having mean life T are observed to have activities AP and AQ respectively at the time of observations. See, both are same material means having same decay constant. Correct here. Having same number of initial nuclei. Asked here at any instant of time, at a given instant of time, see, having mean life T are observed, have activities AP and AQ respectively at the time of observation. If P is older than Q, then the difference in their age is, assume here, AP and AQ respectively are activity, because activity are not same. Because one is older than the other one, rate of decay is same. Isn't it? Here see, AP, what is AP? AP is equal to what? A naught into e to the power of minus lambda into T1. Because lambda is remain same. So, not T1 at the time of observations. Just a minute. It is after the time T. Correct here. So, e to the power of minus what? Lambda into T. Similarly, AQ is given by, T1. So, AQ is given by A naught into e to the power of minus lambda into T2 students. Because P is older than Q. P is older than Q. After the time T1, see, at the time of observations, P is older than Q. See, after time T1, AP is equal to A naught e to the power of minus lambda T. AQ is equal to A naught e to the power of minus lambda into T. What is asked here? Then difference in their age is, that is asked here, T1 minus T2. Isn't it? See, initially they contain same number of nuclei. Therefore, AP divided by AQ is given by, what is AP divided by AQ? AP by AQ is equal to what? E to the power of minus lambda into T1, isn't it? Divided by e to the power of minus lambda into what? T2. Got it? That is given by, take reciprocals on both sides. Reciprocals on both sides. That is AP divided by AQ is equal to what, students? AP by AQ is equal to e to the power of what? Any doubt? So, e to the power of what? Minus lambda into T1, lambda into T2. Isn't it? E to the power of lambda into T2 divided by e to the power of lambda into T1. Lambda into what? T1. Any doubt? See here, AP by AQ is equal to, that is e to the power of what? Lambda into T2 minus T1. We need what? T1 minus T2. Okay. T2 minus T1. E to the power of lambda into. But we need a difference between their ages. That is what? Lambda into T2 minus T1 is equal to, lambda into T2 minus T1 is equal to what? lambda into T2 minus T1 is equal to what? Lambda into T2 minus T1 is equal to ln of AP divided by AQ. Ln of AP divided by AQ. Ln of AP divided by AQ. But asked here what? P is older than Q. I need what? T1 minus T2. T1 minus T2. Right? Remember. So, I will change later. T2 minus T1 is equal to 1 divided by lambda into ln of AP divided by AQ. Ln of AP divided by AQ. Got it here? Ln of AP divided by AQ. So, what is T1 minus T2 is what? T1 minus T2 is given by T1 minus T2 is equal to what? T1 minus T2 is equal to 1 by lambda. What is 1 by lambda? Mean life. That is T1 minus T2 is equal to T into, I took say T2 minus T1 equal to ln of AP by AQ. So, T1 minus T2 is equal to what? Ln of AQ divided by AP. So, good answer is what? Ln of AP divided by AQ. AQ by AP, sorry. T1 minus T2 is equal to T into ln of AQ divided by AP. So, good answer is what? B. Right answer is the B. AQ divided by AP. Any doubt? See, AP is equal to A0 e to the 4 of minus lambda into T1. Right, similarly. AP by AP is equal to what? E to the power of minus lambda into T1 e to the power of minus lambda into T2. Isn't it? We got here. Now take reciprocals. Reciprocal lambda T positive. See, goes to numerator, denominator. Then take what? Logarithmic rule. Lambda into T2 minus T1 is equal to ln of AP by AQ. Then T2 minus T1 is equal to 1 by lambda into ln of AP by AQ. So, we need what? T1 minus T2 because T1 is the age of the what? P. See, after a time T1 minus T2 is equal to 1 by lambda is what? T ln of AQ divided by AP. So, good answer is what? B is the right answer. B is what? Right answer. I hope you understood this question, students. I am going to last question of my discussions. So, what is given here? A radioactive nucleus, initial mass number A and atomic number Z emits 3 alpha particles and 2 positrons. Emits 3 alpha particles and 2 positrons. Got it? The ratio of the number of neutrons to that of protons in the final nucleus will be. See, what is asked here? Initial mass number A, atomic number Z emits 3 alpha particles, students. Okay, now I am going to discuss about that. First, number of neutrons. Number of neutrons. Number of neutrons. I am take the what? Capital letter N. Okay, number of neutrons. See, because of the emission of the 3 alpha particle, we know what is alpha decay. When the nucleus of the radioactive element emits alpha particle, newly formed element has atomic number less by 2, mass number less by 4. It means that decrease in proton number by 2 as well as neutron number by 2. Because of the emissions of the 3 alpha particle, decrease in neutron number by 6. So, N is equal to what we know? A minus Z minus 6 because of the emission of the alpha particles. And 2 positrons. Emission of the positron means nothing but what we know. What is positron? Positive beta particles. So, when the nucleus of the radioactive element emits a positive beta particle, it means that proton convert into neutron. Proton convert into neutron. It emits 2 positron means 2 neutrons are created. Therefore, plus 2. Isn't it? Plus 2. Therefore, A minus Z minus 6 plus 2. That's equal to what, students? A minus Z minus 4. A minus Z minus 4. Come to the alpha particles. Number of alpha particles. Got it? Number of number of protons. Number of what? Protons. Number of protons. Number of protons. Got it? See, number of protons. Say Z is equal to. Not Z. Take number of protons as a P, okay? Because Z stands for your atomic number. Okay, number of protons, okay, I'm taking like this. Number of protons is given by, see, because of the emissions of the 3 alpha particles, there's a decrease in proton by 6. Therefore, Z minus 6. Again, it emits 2 positrons, isn't it? 3 alpha particles and 2 positrons. So, as it emits 2 positrons means 2 protons convert into neutrons and positrons. Therefore, it emits 2 positrons means there is a loss of proton by 2. Therefore, Z minus 6 minus 2, that's equal to what? Z minus 8. Now, what is asked? The ratio of number of neutrons to that of protons in the final nucleus will be. So, ratio of the number of neutrons A minus Z minus 4 divided by Z minus 8. Therefore, A minus Z minus 4 divided by Z minus 8. I hope students understood this question. I hope all of you understood what I taught today in my sessions. Okay, still, do you have any doubts? Please contact me by using my mobile number. Don't hesitate to ask because you are the students, isn't it? So, write well in competitive exams, get good rank. Wish you all the best. Okay, I think I am finished my class at this times. Okay, thank you one and all. Thank you, thank you. ಆಯಿತು.